moving on from where we stopped, we said given that differential equation, question says that write a series solution for the differential equation. Write a series solution for the differential equation, right? We said our first step is what? Determine the nth derivative, meaning find the nth derivative for that differential equation. That's the first step. Step 2, substitute x equals to 0 in your nth derivative so as to get the what? Recurrence relation. And we've gotten the recurrence relation. This is what we got, right? Then the next step is what? We call the Maclaurin power series equation, or you say we call the Maclaurin power series solution. That's the third step. The fourth step, solve for the higher derivative of y. Solve for the higher derivative of y. When we say higher derivative of y, meaning your derivative starting from the second derivative, the third derivative, the fourth derivative, and so on and so forth, right? Meaning continuously. Then take note that this higher derivative must be in terms of what? Y and y prime, right? We said take note that this higher derivative must be in terms of y and y prime, right? So this is our second, meaning out of all these steps, we've only done step 2 so far. Out of all these steps, we've only implemented the first 2 steps so far, right? So meaning step 3, we call the Maclaurin power series solution. By Maclaurin power series solution, we are saying that y which is equals to f of x, y which is equals to f of x is equals to y. Take note that y is still the same thing as you writing y naught, y prime is still the same thing as you writing y prime naught. Meaning from this Maclaurin series solution, I'm having y plus the first derivative multiplying x, substituting what I have here, meaning I'm saying y naught, y prime naught, right, plus y prime x raised to the power of 2 divided by 2 factorial plus y prime multiplying x raised to the power of 3 divided by 3 factorial plus the fourth derivative y raised to the power of 4 multiplying x raised to the power of 4 divided by 4 factorial plus y raised to the power of 5 multiplying x raised to the power of 5 over 5 factorial plus y raised to the power of n multiplying x raised to the power of n all divided by n factorial. We said we call the Maclaurin power series solution, or you say Maclaurin power series equation. By Maclaurin power series equation, this is what we are referring to, meaning that with this, and the last step now says that solve the higher derivative. When we say higher derivative, meaning your derivative of y starting from 2, meaning your second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, all must be expressed in terms of what? Y naught and y prime naught. So how do we get that? We use recurrence relation. We use what? Recurrence relation. So recurrence relation, that's what it does. It helps us to find the second derivative, third derivative, or you say in general, it helps us to find the higher derivative of y in terms of y naught and y prime naught. And also take note that some question will be specific, meaning the question will tell you exactly where to stop. For this very question, we are told to stop at the 6th power of x. We are told to stop at what? The 6th power of x. Meaning I'm having y raised to the power of 6 multiplying x raised to the power of 6 divided by 6 factorial. What if the question says that stop at the 7th power of x, meaning plus y raised to the power of 7 multiplying x raised to the power of 7 all divided by 7 factorial. So meaning given a question, so in essence what that means is that given a question you have to watch out for the necessary conditions, right? So for this particular question, the question says that stop at the 6th power of x, meaning I'm stopping at this 6th power of x. By 6th power of x, I need to express y prime, y raised to the power of 4, y raised to the power of 5, and lastly y raised to the power of 6, all in terms of what? Of y naught and y prime naught. So that's what it means, right? Now, how do we get all these higher derivative of y? Substitute the value of n. Substitute the value of n equals to 1, 2, 3, 4, 5, up to y raised to the power of 6. Up to y raised to the power of 6. right? Substitute the value of n equals to 0, 1, 2, 3, 4, 5, 6, or you say in general, substitute the value of n as real number up to y raised to the power of 6. So meaning, let's solve. So we are saying that using this recurrence relation, when n is equals to 0, when n equals to 0, what do I have? Following this recurrence relation, following your recurrence relation, I am having y all raised to the power of 0 plus 2, right? Equating that to negative all into bracket 0 square, right? Minus 4 multiplying 0 minus 5 multiplying y raised to the power of 0. Any question on that? Multiplying y raised to the power of 0, right? Meaning, simplifying this, what do I have? I have y raised to the power of 2, equating that to negative all into bracket. This becomes what? Negative 5 multiplying y raised to the power of 0. Therefore, y raised to the power of 2 is equals to positive 5 multiplying y naught, which implies 5y naught, which implies this, right? What we have here, by the time we simplify this, you got this, right? This implies this. Recall that when we did the introduction, when we derived it, we said normally mathematically y raised to the power of 0 is what? 1. But when it comes to this power series solution of the ordinary differential equation, you assume y raised to the power of 0 as y. You assume y raised to the power of 0 as y, right? And we also know that y can be written as y subscript 0, meaning y naught. So if y raised to the power of 0 is assumed as y, include your subscript, meaning y naught. So this answer, meaning y raised to the power of 2, we got it as 5y naught. Can you now see what we said? We said solve for the higher derivative of y, meaning y2, y prime, y raised to the power of 4 in terms of y naught or y prime naught. Meaning all these higher derivative is a must. It must be expressed as y naught or y prime naught. So we've done the second one. Now moving on to the next one, which is the third derivative. When n equals to what? When n is equals to 1. You know, I'm stopping at the sixth derivative because the question says that stop at the sixth power of x. What if the question says that stop at the fifth power of x? You stop at the y raised to the power of 5. Or what if the question was not specific? Meaning we are not told what value of x we should stop. Meaning it is our choice. You can stop at any value of x. Right? Now, when n equals to 1, what do I have? Substituting 1 into my recurrence relation. I'm having y, right? Raised to the power of 1 plus 2, meaning y raised to the power of 3, which is equals to y raised to the power of 3 is equals to negative all into bracket. What's n? N is what? 1. Meaning 1 square, right? Minus 4 multiplying 1 minus 5 all multiplying y raised to the power of 1. Any question on that? Now from here, I'm having y all raised to the power of 3 is equals to negative all into bracket 1 minus 4 minus 5 multiplying y raised to the power of 1. Moving on, this becomes negative all into bracket negative 3 minus negative 5 multiplying y prime. Therefore, y raised to the power of 3 becomes negative multiplying negative 8 multiplying y prime, which meaning y raised to the power of 3 is equals to 8y prime when n is equals to 2. The next one is when n equals to 2. Meaning, anywhere I see n in my recurrence relation, I substitute, right? So it becomes what? Y all raised to the power of 2 plus 2, meaning y raised to the power of 4, right? Y raised to the power of 4 is equals to negative all into bracket. What do I have? 2 square, right? Minus all into bracket 4 times 2 minus 5 multiplying y raised to the power of 2. This becomes negative all into bracket 4 minus 8 minus 5, right? Multiplying y raised to the power of 2. Then by the time we sum this up, what do I have? I'm having negative 9 I'm having negative all into brackets minus 9 multiplying y raised to the power of 2, right? Multiplying y raised to the power of 2, which is equals to 9y squared, right? Which is equals to 9y squared. Meaning in this case we got y raised to the power of 4 equals to 9y squared. But this last step is telling us that solve for the higher derivative of y, meaning y prime, y prime prime, y prime prime prime, y raised to the power of 4, y raised to the power of 5 in terms of what? Y naught and y prime naught. So once we've gotten this y raised to the power of 4 as 9y squared, what does it mean? This very guy must be expressed in terms of either y prime or y naught. Recall that y raised to the power of 2 is what? Y raised to the power of 2 is what? We've subtracted y raised to the power of 2 as 5y. If y raised to the power of 2 is 5y, it means y raised to the power of 4 becomes what? 9 multiplying 5y naught, right? And this gives us what? 45. This gives us 45y naught. Right? So we've solved for when n equals to 0, we got y raised to the power of 2. We solve for when n equals to 1, we got y raised to the power of 3. When n equals to 2, we got what? Y raised to the power of 4. But the question says that stop at the 6th power of x, meaning y raised to the power of 6. So let's substitute. Substituting n equals to 3 and substituting n equals to 4. When n equals to 3, right? Meaning anywhere I see n in my recurrence relation, what do I substitute? 3. So it becomes y raised to the power of 3 plus 2, which is equals to y raised to the power of 5 equals to negative all into brackets 3 square, right? Minus all into brackets 4 times 3 minus 5 multiplying y raised to the power of 3. This becomes negative all into brackets 9 minus 12 minus 5 multiplying y raised to the power of 3. Solving this, what do I have? I have negative all into brackets minus 8 multiplying y raised to the power of 3. This multiplying this, I have 8y cubed. Meaning we got y all raised to the power of 5 as 8y cubed. And we said all higher derivative must be a function of what? Y and y prime. So if I'm getting y raised to the power of 5 in terms of y cube, meaning I have to substitute y cube, I have to express y cube in terms of what? Y naught or y prime. Recall that y raised to the power of 3 was what? 8y prime naught. Therefore, y raised to the power of 5 becomes what? 8 multiplying 8 multiplying y prime naught, which is equals to what? 64 y prime naught, right? This is when n equals to 3. When n equals to 3, we got y raised to the power of 5, which is equals to 64 y prime naught. Moving on, when n equals to what? 4. Substitute, anywhere you see n, substitute 4. Anywhere you see n in your recurrence relation, substitute it as 4. So meaning you have y raised to the power of 4 plus 2, which is equals to y raised to the power of 6, which is equals to negative all into bracket 4 raised to the power of 2 minus 4 all into bracket 4 minus 5 multiplying y raised to the power of what? 4. This becomes y raised to the power of 6 is equals to negative all into bracket 16 minus 16 minus 5 multiplying y raised to the power of 4. This cancels out. I'm left with what? 5y all raised to the power of 4, right? This multiplying this, we got 5 raised to the power of 4. So meaning from here, y raised to the power of 4, substitute y raised to the power of 4. We got y raised to the power of 4 as what? Y raised to the power of 4. Y raised to the power of 4 is what? Y raised to the power of 4 was what? 45 y naught, right? Therefore, y raised to the power of 6 becomes 5 multiplying 45 y naught, which is equals to 225 y naught, right? So from here we solve for, meaning we've gotten y prime prime, y cube, which is the third derivative, y raised to the power of 4, y raised to the power of 5, and y raised to the power of 6, right? Meaning it can go on and on, right? Meaning it can go on and on, meaning it can stop at any value of y. It can stop at any function of y. But this question was specific, telling us what function of y we should stop, meaning the derivative of y that are going to stop. right? So the question says that stop at the 6th power of x. By 6th power of x, meaning y raised to the power of 6. And even if the question was not specific, you can stop at any value of x, right? Meaning you might have stopped at y raised to the power of 5, y raised to the power of 4, or y raised to the power of 3, right? It's our choice. You can stop at any value of x, right? So moving on, let's substitute what we've gotten back to our Maclaurin series equation. We substituting, it becomes y, meaning f of x is equals to y naught, right, plus y prime naught multiplying x plus y prime prime. What did we get as y prime prime? That was 5y naught, right? Meaning plus 5y naught multiplying x squared all divided by 2 factorial, right? Y prime prime was what? The third derivative was what? What do we get when we did that? That was 8. For the third derivative, positive 8 or negative 8? We got positive 8y prime naught multiplying x cube over 3 factorial. Moving on, y raised to the power of 4. We got y raised to the power of 4 as what? 45 y naught multiplying x raised to the power of 4 over 4 factorial. The next one, y raised to the power of 5 was what? Y raised to the power of 5, we got 64 y prime naught multiplying x raised to the power of 5 over 5 factorial. Lastly, for y raised to the power of 6, we got 225 positive 225 y naught positive 225 y naught multiplying x raised to the power of 6 over 6 factorial. Any question on that? Any question? So meaning that given that differential equation, it says that find the meaning given that differential equation, question says that write the series solution of that differential equation. Meaning this is the series solution, this is the series solution, but you can collect like term from this series solution, meaning separate the function of y naught from the function of y prime naught, meaning we have two series solution, right? And that's the base of Frobenius equation, right? That's the base of Frobenius equation. When we say Frobenius equation, we just move a step further with what we've done so far, meaning we go a step further, right? You know, have it in mind that Frobenius equation is just telling us that we are multiplying, let's say you have y, you also want to write, given a question, given a differential equation, let's say you are given a differential equation, question says that find the series solution. The question will tell us that find the series solution. We will not be told the particular series solution to perform. Is it power series solution or Frobenius equation? How do you identify, given a differential equation, how do you identify that I'm to use either Frobenius equation or power series equation? So the difference between power series and Frobenius is that you have your y. You know, in this case, this is our Maclaurin series. In series solution, you can write this Maclaurin series as y equals to summation from r equals to 0 x multiplying c, right? In series solution, you have this. Say this Maclaurin solution, you want to write it in terms of series solution. This is the series solution, meaning you are summing all this up. You are summing all of this up. This is the series solution, right? That's what power series solution means. But Frobenius is telling us that y is equals to x raised to the power of r multiplying by power series solution, meaning that summation from r equals to 0 x raised to the power of c, right? By directly performing this is what we have. We then have summation from r equals to 0. We have infinity. There is infinity here. This is our infinity. It is telling us that summation from r equals to 0 to infinity multiplying x raised to the power of r plus c, meaning that y is equals to this. So this is Frobenius equation. While this is power series solution. So you'll be given a differential equation. Given that differential equation, how do you identify the series solution method to use? Am I using power series solution or am I using Frobenius equation? Meaning we have to identify if Frobenius equation is valid. If Frobenius equation is valid, you use Frobenius. If it is not valid, you then use power series solution. So we are going to see that in the next example. Back to what we have here. Let's collect like term, meaning separate the function of y from the function of y prime naught, right? By doing that, it becomes, meaning I have y equals to y naught all into bracket 1, right, plus 5x squared all divided by 2 factorial, right, plus what's the next term? Plus 45 x all raised to the power of 4 all divided by 4 factorial plus 225 plus 225 x raised to the power of 6 all divided by 6 factorial, right, plus y prime naught all into bracket x plus 8s cube over 3 factorial plus 64 x raised to the power of 5 over 5 factorial, right? Meaning that given this differential equation, which was 1 plus x squared y prime negative 3xy prime minus 5y. Given this differential equation, you want to write the series solution for this differential equation. This is the series solution. But you observe that this series solution, you are having two solutions. The first solution is for y naught, while the second one is what? For y prime naught. In some cases, you'll be given boundary condition. When we say boundary condition, meaning we are giving the value of y and we are also giving the value of what? Y naught. We are giving the value of y and we are also giving the what? Value of y naught. Now let's say we are giving boundary condition for this question. Meaning, given this differential equation, we are also told that y equals to 2, right? And y prime, okay, and dy dx is equals to 3, and dy dx equals to 3. What this means is that if y is equals to 2, it means y prime is equals to 3, and this implies that y naught is equals to 2 and y prime naught is equals to 3. So with what we have up to this level, substitute. By that we substitute, this becomes what? This becomes 2. Y, the other one becomes what? 3. Y, the other one becomes 3. But in a case whereby you are giving y equals to 1 and you are giving y prime naught, equals to 1. Meaning I'm having invisible one here, right? You can still write this as A and you write this as what? B, right? Let's say this was the boundary condition given. I'm having invisible one. That invisible one, you can imagine it, or you say you assume it as A and you assume this as B. Given a question, find the series, meaning given a differential equation, find the series solution of the differential equation. This is your step. The step remains the same. First step is what? Obtain the nth derivative, right? Once you obtain the nth derivative, step 2 is what? Step 2 is substitute 0 equals to the nth derivative so as to get the recurrence relation. Step 3 is what? Step 3, what was step 3? Step 3 is we call the Maclaurin series power solution. Then step 4 is express the higher derivative, meaning y2, y3, y raised to the power of 4, y raised to the power of 4 in terms of y naught and y prime naught. Once you've done that, input values into your Maclaurin series solution. Then collect like term. When we say collect like term, separate the function of y naught from the function of y prime naught. Then you obtain what you have. Meaning the steps remain the same for any given question. So this is the whole idea of power series, Leibnitz Maclaurin series. But for Frobenius equation, what Frobenius equation does is that it helps us to understand a particular differential equation. Say you are given a differential equation. How do you identify if you have to use power series, Leibnitz Maclaurin series? How do you identify if you have to use Leibnitz Maclaurin series or you have to use Frobenius equation? Are you getting that, bro? I said what Frobenius does is that it helps us to understand a differential equation given. Say you are given a differential equation, how do you identify that this differential equation given to me, I'm to use Euler series solution or I'm to use Frobenius equation? So we have theoretical explanation to it. So once we understand the theoretical explanation, we are good to go. Meaning, given a differential equation, we are going to know if I'm to use Euler series solution or I'm to use Frobenius equation. Just take note that generally Frobenius equation is written as a of x multiplying y prime prime plus b of x multiplying y prime plus c of x multiplying y, equating this to 0.